last question is going to be something about given sums, and it's going to be one question. Now you can discuss the question with your neighbor in the notes. So we're talking about this function, and the region we're integrating over is the region from -2 to 4. So it's these two shapes. And the integral is just, though, as we said last time, it's the signed area of this shape. Well, the whole function lies above the x-axis, so both contributions are going to be positive. And the contribution from this triangle is 2 times 2 also is area 2. This triangle is area 4 times 4 divided by 2, which is 8. And the total area is 2 plus 8, which is 10. So, if, however, we want to integrate the function just x dx from -2 to 4, we would have a different picture. The function would be like this. The triangles still will have the areas of 8 and 2, but now the integral will capture this area with sign minus, because the whole function lies below the x-axis. So this is within 8 minus 2, which is 6. So plus 8 minus 6. Okay, so any questions about this simple question? So let me remind you that last time we defined the definite integral, thing like this, in 2 ways. One was using frequent sums, another one was using combination as an area, signed area, and so a reminder. So to define this limit, this integral as a limit of number of subintervals goes to infinity of the volume sum. Sum in 10 terms of the value of the function at some point at k in the case subinterval times the length of the subinterval, and where the length of the subinterval is t minus 8 divided by n. So divide the integral from a to b then r, and indicate point which we evaluate the function lies in the case subinterval. So this is a plus a minus 1 times delta x, a plus a delta x. And for most reasonable functions, for functions which are continuous, they are piecewise continuous, such a limit exists. Such sums converge to some number, and this number is called the integral. And we gave interpretation of this as the sign area under the graph. So it's a little bit kind of confusing to say it's the area under the graph of f, because it's more precisely it's the area between the graph of f and the x-axis, and the sign here will explain except for this effect. Whatever is below the x-axis comes with the negative sign. And last time we started discussing properties of this procedure of integration. We discussed the following properties. Property 1. If you want to evaluate the integral from a to b, you can do it in 2 steps. Use a point between, so c, and integrate first from a to c, then from c to b, and get the result. And that was just about splitting the total area into 2 parts. The area from A to C, and then from C to B. And Another property that we started discussing but didn't finish, integral of some two functions is the sum of the integers. And in the very end of the class, we discussed how this can be applied to some integral of very complicated function, 1 plus sin x, if I remember correctly. And you see that geometrically, at least, this statement is not that obvious. I mean, you can find some interpretation, but geometrically, it's not really obvious. Something about area under the graph of f plus g being related to area under the graph of f and the area under the graph of g. Not really obvious. But using this definition, it becomes quite obvious because the Riemann sums on the left and on the right are exactly the same. So the explanation here, it's not even about the linear procedure, it's about the sums themselves. The sum of this function times delta x is the same as sum of fk delta x plus the sum of g of xk delta x. So in this equation, I'm just rearranging the order of summation. Here I'm taking, in each sum I'm taking the value of f, adding the value of g, and then taking the sum of the results. And here I first find the sum of all the values of f, then I find the sum of all values of g, and then take the sum of the results. But of course we know that the result of summation doesn't depend on the order. So each Riemann sum for this and for that is exactly the same. In particular, the limits, the integrals are also the same. So algebraic step is quite obvious. Another fact, if you have a number then integral of c becomes a function. So you can take the constant out of summation, and as well you can take the constant out of integration. But be careful, c should be a number, not a variable, not a function of the variable, just a number, 5, 10, something like this. So, for instance, integral of 5x, x, from 0 to 1. So it's 5 times the integral from 0 to 1, 30x, according to this property. And the integral of x dx from 0 to 1 is a small interval. So it's 5 times 1. So admittedly, we know for now really a small, we know how to relate really a small amount of integrals. These are the integrals of functions which are related to simple geometrical shapes, like lines, like circles maybe, but more or less that's it. We don't really know any other. For instance, we can't even for now conclude what's the integral of x squared. And the problem is, well, integral is defined as an infinite sum. And we don't really know that many sums. So if we learn to evaluate some sum, well, then we can evaluate corresponding integral. So So let me give you an example. I'll tell you something about a particular sum. So if you want to evaluate the sum of the first n squares, 1 squared plus 2 squared plus 3 squared up n squared, the answer turns out to be n times n plus 1 times n plus 1 over 6. So it's a formula that I will not explain. It's a formula that you can, well, if you see it, you can try to prove it by reduction. If you didn't see the right hand side, you can try to guess it and then prove it by induction. Or there's several different proofs, non-applications. But anyway, this formula is correct. Like when n is equal to 1, the right hand side tells you 1 squared, the right hand side tells you 1 times 3 times 2 over 6. So the image. We'll find the image for every value of n. So now we know this sum. This knowledge can be used to evaluate an integral from 0 to 1 x squared dx. This integral is, well, less obvious than the integral like this. It's not about a straight line, it's about a parabola, area under a parabola. Geometrically not quite obvious what it is. So it's about such a shape. And its area. Well, let's write down the definition of this integral. First of all, it's a limit that goes to infinity of a particular sum from k from 1 to n. Now let me choose, let's say, right Riemann sums. So subdivide the interval from 0 to 1 to n equal subintervals. And the right endpoint of kth one is going to be k over n. At this point, k over n, I will find the value of my function and multiply it by the length of the subinterval, which is 1 over n. So if you want to relate this to that, so this term is f of k, and this term is f of x. So now we know what this integral is in terms of its basically definition. It's limit of sub-Riemann sums. Now let's try to find this sum. First of all, I can write it as k squared divided by n cubed. I just open the brackets. Next step is to realize that this factor of n cubed is common to all the sums. So I take at each step some function of k, namely k squared, and multiply it by the same number, 1 over n cubed. So this number 1 over n cubed will be pulled out of this summation. Write this as limit that goes to infinity of 1 over n cubed times the sum of k squared and 1 squared. And now we encounter the question of what is the sum of the first n squares in the one. So I just provide you with the answer. So what it is? n plus 1, n plus 1, divided by 6. And finally, the limit. And of course, as n goes to infinity, this goes to 1. So now we do know this theorem. We know that as n gets larger and larger, this sum gets closer and closer to 1/3, and in the limit we get the area is precisely 1/3. So out of this 1 unit square, 1/3 of the area lies below the parabola. There is a problem with this approach, which is given in the first line. I told you that somehow, well, I found that the sum is such and such. I found a closed expression. I found a formula that expresses this sum for any value. And of course, in general, you should not expect to be able to do this easily. If you try to find even the sum of, I don't know, fifth powers of natural numbers, it's going to be a pretty complicated expression. If you want to find sum of sine of k over n, it's going to be even more complicated. So the more complicated your function, the more complicated the sum that you will encounter, the more complicated will be the evaluation of the sum, and the integration is going to become nightmare. So this is a good example of how you can apply the definition in one particular example, but it's not going to really ability to integrate functions. So before we go to the actual rules of how to integrate stuff, the questions about this. K over n squared. So I subdivided the integral from 0 to 1. I have the integral from 0 to 1. I subdivided to n equal parts. So we have 1 over n, over n, over n, and sum over n, and 1. And I choose the right hand point. So what is the case? Right hand point, it's k over n. This one? So from here to here? Oh, here I just factored out 1 over n, and then I rewrote n plus 1 divided by n is 2 plus 1 over n, and n plus 1 is 1 over n is 1 plus 1 over n. So I factored out the equivalent terms. So here the equivalent is n, that's n, that's n, that's over n, and so So let's now talk about k over n. So k over n without the square. K over n is this xk. It's the right endpoint of the case subintegral. And then I look at this integral from 0 to 1. It's divided into n equal parts. And I ask the question, what is the coordinate of the case right endpoint of the right endpoint of case subintegral? So for the first one, it's 1 over n, the second one is 2 over n, the case endpoint of the case. And after this, I evaluate my function, which is very this one. Okay, so let's now discuss what is the main tool of integration. It's called the fundamental theorem of calculus, and you'll see in a second why it's such a grandiose name. something which looks like a strange thing to do. So let's consider we'll start by doing a seemingly strange thing. We'll consider the integral of a function. I choose to call my variable t, for a reason that will come here in a second. I'll compute this area from the endpoint, from the starting point A to some point x. And I'll call the result f of x. So let me explain what I'm doing. Instead of finding just one area, I'm going to find lots of different areas for different points x. So I'll fix a point A, and I let my point x to be some point, let's say to the right, to the left, okay, it doesn't matter. Then I have my function f, and I'll compute the area from A to x. So I'll compute this area. The strange thing about what I'm going to do is, I'm not going to compute just this one area for one particular value of x. I'm going to think about x as something, as a quantity that can change. So compute how this area changes with x. And I'll call this dependence f of x. So for each particular value of x, f of x is this area, the area under the graph t from A to x. Okay, yes, I can of course compute this area for any particular value of x. What do I get out? So the next observation is quite interesting. It turns out that the derivative of this function is exactly my original function. Let me explain this one. What is the derivative of some function d f of x? Well, it's approximately the difference between the value of the function f x plus a small change minus the value of this function f x and divided by the change. So the derivative is more or less f of x plus small change delta x minus f of x divided by delta x. So the derivative is exactly the limit of this expression as delta x goes to 0. Now, what is it for our function, big f of x? Let's interpret this geometrically. So big f of x was delta x, so let's have a x and x was delta x. The value of f at the point x was delta x is the area from here to here. The value of f at the point x is the area from here up to here. What's the difference? Can I see it on the picture? Yes. So the area up to here minus the area up to here is what's being added. So it's this area. This area is exactly f of x plus delta x minus f of x. Now I'm taking this area and dividing it by delta x. Well, but this area, this thing is really thin rectangle. It's almost a rectangle. This thing is a little bit curved, but not really that much. So So the difference between this and the actual rectangle like this is quite small. So this area is approximately the base of this rectangle times its height. What's the height? The height is exactly equal to this. The base is delta x. So overall, if you take this area and divide it by delta x, you're going to get an answer which is quite close to f of x. So this thing, the area in the numerator is more or less the area of the rectangle, f of x delta x. Denominator is delta x. So the whole portion is pretty close to f of x. And as delta x becomes smaller and smaller, our approximation becomes better and better. This rectangle, well, this curvilinear rectangle becomes closer and closer to the actual rectangle. This small difference in the two areas, the area of rectangle and the area of curvilinear rectangle, is getting smaller and smaller. So in the end, we get this result. As delta x becomes smaller and smaller, this expression, which you call derivative of df x, turns out to be the original function, the function that we were integrating. Already this is quite curious. So somehow this procedure of finding the area under the curve of f produces for you a function whose derivative is f of x. Now let's think through the consequence of this step for actually finding the area. So suppose that I don't know what the area is. I can't evaluate this now. But suppose I somehow found a function with this property. So suppose somehow we found a function that we call f tilde with the property that its derivative is the original function of x. So we already know one function for which the derivative is exactly f of x. It's this function. Integral from a to x of f of t dt. So these two functions have the same derivative. Their difference must have derivative equal to 0. So their difference must be not changing, must be some constant. So then this function isn't the same as that function over there, but maybe plus some constant. So they have the same derivative, they change it at the same rate, but maybe there is some difference between those. How do I find this constant? Well, let me just find the value of this function at some point. So 1, 2. I don't really have that many points at which I can actually evaluate this function here. In fact, there is just one which I'm pretty sure what the value is. When x is equal to a, I'm computing the area from b to a. What is it? 0. There is no area. So let me plug in x equal to a. Then I'll find that f tilde of a is equal to 0, the area from b to a, plus c. So this constant is exactly the value of the function of tilde Okay, so how does all this help me? Well, here's how. Suppose I want to relate this integral from a to b of f of t dt. I already know that it is more or less by definition the value of large f at the point b. But now I have an alternative expression. It's the value of f tilde at the point b minus the value of f tilde at point a. Because my function big f is just f tilde minus f tilde at point a. And now I have a prescription how to find the integral of functions. How to find the area under the graph of function from a to b. The prescription is as follows. Step 1. Find by some means a function whose derivative is my function. Once you found it, here's the answer. The difference of the value of this function at the endpoints in a. So let me summarize this whole discussion in one theorem, which is called the fundamental theorem of calculus. I just want to have it stated. So theorem. First part. If you consider the function integral from a to x, f of t dt, as a function of x, you find the derivative with respect to x. You are going to reconstruct your function. Second part, being prime of x is equal to x. If you found some function with derivative equal to f, then integral from a to b f of x dx is equal to f of b minus f. Sometimes we also call this expression f related to x equal to a and x equal to b. So this is just a notation which stands for the difference. F of b minus f of a. And this theorem, well, it establishes a funny, a really surprising link between integration and differentiation. So integration, we started with the question how to find the area under the graph of some function. So seemingly a question which has nothing to do with differentiation. Differentiation, what was it about? It was about the rate of change of our function at a certain point. So here are two ways. If you take a function, first integrate, and then differentiate the result expression, we are going to reconstruct the function. So integrating and then differentiating produces the original function. Another way, if you integrate function which is derivative of something, you are basically going to reconstruct this term. You are going to reconstruct the difference with something at two points. So if you are integrating the derivative, you are basically getting the same thing. So it tells you that differentiation and integration are, in a sense, opposite operations. Let's look at some examples of how this theorem is being used. let's compute once again this integral x squared from 0 to 1. So instead of using the definition of limit of reconciles and so on and so on, I'll try to use this theorem. I know that to find this integral, I can proceed as follows. First, try to guess a function whose derivative is x squared, and then evaluate the difference of this function at 1 and 0. So, what function would have a derivative which is x squared? Yes. So if you differentiate x cubed, you're going to get 3x squared. If you want to get exactly x squared, you will take x cubed and divide it by 3. And then according to this theorem, the difference of this function x equal to 1 and x equal to 0, which is 1 equal to 3 and 0 equal to 3, is 1/3. That's it. No evaluation of sums, no geometrical reasoning, nothing. Just a guess of a function whose derivative is x squared. So we see that now it becomes really important to have a way to find, given a function small f, to find some function whose derivative is this small f. Any questions about experimental theorem of outputs? Yeah. What is 1/3? Where it comes from? What does it mean? Well, the mean is still the same. We are still computing the area from 0 to 1 under x squared. So the mean is exactly the same execution. We are still doing the same operation. We are still computing the area under 1. But now we have a better tool. Instead of doing it using Riemann sums, we use the argument using this theory. We get exactly the same answer, that 1/3 of this area of this unit square lies below the parabola, but we get it in a much faster way. So it seems that the operation of taking a function and finding a function whose derivative is this given function is quite important. And we give it a name. We call the indefinite integral. So it's basically just notation. The provided notation is very good. So we say if the derivative of some function is equal to x, then the relation between f and the function small f is like this. We call the large f an antiderivative or indefinite integral of f of x. And usually when we write this expression, we mean not just one antiderivative, but all possible antiderivatives, which means all possible function big f of x for which the derivative is small f of x, and we know that we add a constant, we don't change the derivative. So we have this notation. Once again, this is not the integral that we encountered before. It's not the area. It's just a new notation which tells you the derivative, or rather, all functions whose derivative is small f of x are large f of x, maybe plus a constant. Just a notation. So this thing is called indefinite integral starting with the function, finding the function with derivative of this function, and evaluating this interface. So in fact, these two things are very much related. And now let's build some vocabulary of functions for which we do know this antiderivative. And it's going to be more or less taking the vocabulary of derivatives and looking at it in the opposite way. If you know the derivative of something, we'll try to find the antiderivative, which corresponds to it. So some integrals. First integral of x to some power. So we are trying to find a function whose derivative is x to the power n. Well, it's exactly the same task as it used to be for x squared. So we know the derivative of x to the power n plus 1 is n plus 1 times x to the power n. Well, I don't want this n plus 1, so we divide by n plus 1. This formula works every time when n is not minus 1. When n is minus 1, I can't really divide by 0. So it holds the condition that n is not minus 1. And then what happens when n is minus 1? X to the power n becomes 1 over x. And what function has derivative 1 over x? Logarithm, yes. So it's 1 of x plus a constant. There is a small problem with this function logarithm. It's only defined for positive values of x. For negative value of x, you can check that logarithm of negative x has exactly the same derivative. So overall, we write logarithm of absolute value of x. It has derivative which is 1 over x for both positive x and negative x. Unfortunately, it doesn't work as x equal to 0, but well, this function is something we define with x equal to 0. Okay, so one integral, another integral. Let's have some other simple integrals. Integral of p to x dx. That's the simplest one. What function has derivative p to x? P to x. What other derivatives we know? Well, we know derivative of sine, derivative of cosine. We know derivative of sine is cosine, derivative of cosine is negative sine. So let's convert it to the knowledge of integrals. Integral of sine. So what function will produce derivative which is sine? So cosine will produce negative sine. So it is negative cosine. What function is a derivative of cosine? Sine. And before we finish this list, I'll recall one more important function. Function whose derivative turns out to be 1 over 1 plus x. Does anyone remember a function whose derivative is 1 over 1 plus x squared? So, is the function arctangent? I'll recall this. So arctangent is the inverse function of tangent. And tangent is sine over cosine. So reminder. short reminder. We say that, so the arc tangent of x is the value y, whose tangent is x, and we slice it to negative by the drop arc tangent looks like this. And this function tells us the derivative 1 over 1 plus x. I will get the knowledge about derivative arc sine and arc cosine. Turns out we will be able to do without them. Okay, so this is our basic vocabulary of integrals, which you should basically just remember. Every time you see an integral of x to some power, use this formula. Integral of 1 over x, use this formula. Integral of sine, and so on.